Welcome to the Cimatron webinar. Today we're going to be reviewing 5 ways to increase progressive die design quality and productivity. Let's meet the team that'll be presenting. Ralph Picklow is our Director of Sales, based in Michigan. Mazen Keju is our Regional Sales Rep for the Eastern United States. David Lindeman is the Senior Applications Engineer who will be presenting the demonstration to you today. And I'm your host, Dan Marinac, Product Strategy Manager for Cimatron. Cimatron is CAD/CAM for tooling. We were founded in 1982. There are currently over 42,000 licenses active in the world. We're known most famously for Cimatron Mold, Cimatron Die, and Cimatron CAM, the 3 pillars of our business. This is a comprehensive CAD/CAM solution for the mold, tool, and die makers globally. We can break our package down into being just CAD, special applications such as Cimatron Electrode for specific applications for the mold industry, and again as a completely integrated CAD/CAM system. The tool maker's challenges: reduced delivery time, improve tool quality, reduce costs, and increase productivity. These are global goals that every tool maker faces. Cimatron is a connected, dedicated software for design and production of molds, tools, and dies. It helps you by automating design and manufacturing of tools to produce final parts quickly and accurately. Starting from sketches, you can completely build your 3D design, or of course import any industry standard design, and even custom translators from major OEMs. From there, you'll work with dedicated die design tools to speed the process of die design, which you'll see here today. Again, completely integrated is 3 5-axis CAM software to create your G-code, and from there you can go direct from CNC to die production. All aspects of the die process are understood and have packages to address it. We're going to be spending this in the first part of 3 series. There's 3 webinars in this series. This is part 1, where we'll focus on die design and give a few hints on the manufacturing side. Look for future webinars with respect to die estimation and die simulation. Cimatron is again a fully integrated CAD/CAM solution dedicated for the design and manufacturing of molds, dies, and tools. In die, we'll look at a dedicated tool for estimating progressive, transfer, tandem, and line dies. That'll be part 2 of our series, not covered today. We will be showing today FEA-based blank shape development and forming feasibility analysis, dedicated design tools to develop, draw, form, flange, trim, gut, notch, punch, and pierce operations, strip design with ease with material optimization application, FEA-based springback analysis with high-quality morphing and compensation. That portion of this demonstration will be reserved for the 3rd in our series. Smart catalogs for die sets and components. Validate your designs with measurement, 3D explicit simulation analysis, collision detection tools, FEA and ECO analysis tools. Create and reuse drawing templates incorporating customer specifications using dynamic multiple shaded views. A couple of these modules, Cimatron Die Estimator and Altair's Inspireform, are third-party packages and part of the Cimatron process. We'll also be showing some 3-axis machining and automated drilling. These are built-in CAD capabilities in our CAM packages to be able to repair surfaces, cap holes, extend surfaces, etc. You'll see some efficient roughing and high-quality finishing toolpaths. You'll see some feature-based plate machining and automated drilling. We will be showing the automated drilling today. Toolpath validation and machine simulation will be shown. Cimatron also offers offline and server NC calculation engines if you want to offload the computational tasks. Automated and customized reports, direct dedicated post-processors. So today we're going to be reviewing 5 ways to increase quality and productivity. We'll start by assessing the part to be stamped, develop the accurate blank shape. We'll get into strip layout in a fast and efficient process. The advantages of using parametric die set and smart components, and leveraging 3D punches, forms, and cuts. We'll have time for Q&A at the end of the webinar. I'll turn it over to David Lindeman, our Senior Applications Engineer and our die expert. David.
Thank you very much, Dan. As we get into our die demonstration, we're going to first analyze the part. A number of tools are available so that we can better understand the geometry and also the conditions that are involved in manufacturing the part. In this case, we're going to look at the direction analysis, or basically we're checking to see the draft angles on all of those flanges. We're especially trying to avoid a situation where the part may be bent back underneath itself, or there's an awkward forming condition. This better helps us understand at each point exactly what those angles are. In this case, we're looking at the different radiuses of the bends. Is there a bend that's extremely tight? Is it something that's going to be very difficult to hold? Here we want to check for wall thickness. We want to make sure it's consistent, same everywhere. Using the spherical analysis, we can simply touch a point and it measures all the areas where that sphere would connect. Or array analysis, where it shoots a normal away from the face we touch to touch whatever is the opposite face. This way we get a quick and clear analysis of the material. Obviously, we want to avoid a condition that makes it look thicker. We want to check to see if there's anything where the material is being coined. All those things are important to understand. Here with the cross section too, we can take a quick glance and see that it's consistent in any direction. To quickly get some overall measurements, we'll throw this bounding box around it and choose whatever increments that we prefer, or units that we prefer to work with. Again, all this information is reported so that we can get the overall size. It's stepping into forming now. We'll simply add a form shape, which basically is similar to making a duplicate of it. I wanted to decide if I'm working now with the punch side surfaces or the die side surfaces. My preference is the die side. And as I do that, it quickly takes a measurement of the overall wall thickness. That information is then put here into this setup tool, where now we pick the material, which can be from the simple drop-down catalog of materials, or we can always add our own material. And then we set up exactly what we want our clearances to be. So the diagram shows you we're putting in the clearances between the punch and die, how much per each position or plate of that die, what configuration of punch and die do we want. This is now all saved in the setup, and more information, of course, is gathered as we go further along the process, so that with each time we need to form a punch and die, we have the information readily available. Now with this position in mind, we're going to do a crash form, basically an overall quick blank. What are we dealing with when it comes to looking at formability? This allows us to do an FEA analysis where we can check on what areas might wrinkle. Here we're doing a quick check to see on the overall perimeter of the part. Zooming in here, you can see that the blue area is showing where material is gathering, whereas the red shows the potential of how it could be thinning. Here we're identifying wrinkle zones. All right, so we know that there's the tendency to gather material in those corners. All in all, it quickly helps us to see what's involved in forming this part. Moving along, we can simply rearrange this. Maybe I'll push the blank toward the front of it so that I no longer have to look at it close up. But here we're going to go ahead now and start developing out these flanges. So this is going to be a true development where I consider it basically step by step. Working along the one side of the part, we'll tell it that from this area here where we're picking these faces, we want to work with that flange on the left-hand side. So it's just a matter of saying what areas I want to hang on to and then picking the flange. So the system is smart enough to find those areas. It applies the material properties when it comes to the unfolding of that flange, and it'll keep the flange anchored to those faces that we picked initially, like you see here. So quickly it develops out in just a matter of a few seconds. Going further, we'll do the same to the opposite side, and we consider that one station where we're doing the unflanging on both sides. Pick on that again. Spend a few seconds calculating, and then we'll get the result. Each of these stations where we're doing our unflanging, we can do that same FEA analysis and see what the formability is, just doing this one step at a time. That's accomplished. Move on to our next operation. Here in the center, you see there's a dimple. All right, so perhaps that was placed in because we needed to stretch that area, understanding that there's the wrinkle tendency. Let's do that in one single step. So in this case, we'll go ahead and take that out of our sequence of operations. Now we've got our forming condition just for that particular dimple area. Moving on, we'll do another one. Let's work to the inside of that groove. We want to develop the left and right hand sides again. So basically, I'm going to keep that tab where I know I would connect my carrier. Here I'm going to select right down the center and say this is the area that I want to develop to. We'll pick the left side again and now develop it out like that. So I've got the option of quickly getting a blank, quickly getting a form, perhaps for a quotation, where I'm going to pop things into a strip, or I can take a minute or two, like you see here, and develop it out exactly station by station as I want to see it. There, now that form is completed. So here we have what you might call your curved form. We want to lay that out flat and see exactly what it would look like as a true blank. So make sure all the pieces are together here and just do what we call in this case a local blank operation. And it will take the curvature out, laying it flat for me. So I can compare it to the initial blank, or I can go ahead and start working with it as is. Eventually these forms are going to be the things that populate my strip, which I can place in any order I want. It's just a matter up to me how I lay that out. Going into strip design now, we're going to start by nesting. As we do the nesting, we're going to keep track of the utilization. We can keep track of the blank area. Is it going to be a 1-row, 2-row out? As I do a 2-row, do I want to rotate it? Do I need to shift it? Do I need something in the middle, some space for the middle carrier? In this case, a 1 out is fine. I've got the progression that gives me the net utilization I need. We'll go in that direction. Now, how many stations do I want? I'm kind of eyeballing it at this point, but still, again, keeping track of my scrap and utilization. Do I want margins where I start, or gap, say, above and below where I'm going to have my carrier? We'll keep a little extra at the top because we know we're going to need an expandable carrier because of the way this particular part is forming. So that being the case, then let's bring in a carrier from a sketch library. It could be any number of different ways of carrying the part. Here I'm going to do one on the top, one on the bottom, carry the part down the middle. I'll put in my expandable web here. Could be an S curve. It could be a simple expandable carrier like this. Likewise, it could be a straight positioned carrier. Now I'm sketching in quickly a rough idea of where I want my punches to go. So I could be working again finished where I'm placing dimensions to control the location, or maybe I'm quickly sketching like in this case, just because I want to get a quick idea of what this strip needs to look like. Now I'm going through and finding those areas where the punches is going to be. And you can see it's just a matter of doing a single indication. To do it fancy like, I'd probably go ahead and put some radiuses in here. Obviously, I don't want to injure anyone who's working with this die. So we'll do as we call delethalize it. Also, I'll take into consideration some overlapping conditions. Where do I want this first punch to go? You see it punch, and then it carries that hole on down the strip. I'm going to my next region. We're working quick, but you get the idea of how quickly you could put in these overlaps or cookies and then carry on your punch. And again, if I need to make changes, I can reorder where I want those punches to start. Here we'll do a single indication on the bottom area. Zooming up, you can see when I place my, what we call a cookie, that overlap, pick the edge, it knows that edge, it gives me the overlap. Now it's time to punch this one. We'll put it in a the position where it looks like it's the best. Here you see I've got, one more to go. We got the big one here. And again, this might be exactly the type of place where I want to put some radiuses in these corners out here where I'm up against the carrier, and then the cookie to overlap. And I can control that overlap shape and size to whatever I need it to be. Finally, where do I want that to go? We'll place it down here on our fourth operation. And now you can see all that's left is the carrier. So simply put, at this point, we could start popping in those different forms, or we could start making some decisions about what we want to do with that expanded carrier. So in this case, I want to show the carrier pulled open. So to do that, I'm going to go ahead and manage it by working with the sketch. What we could do, and we'll show you that later, is take it through analysis so I can actually see how it's going to be stretched. I'm confident it's going to work. So if I want to quickly keep moving ahead, I'll just keep moving ahead. Now you see I'm populating the forms where they need to go inside of the different positions here on the strip. We'll bring in my carrier one more time. I'm sorry, the stretch web one more time. And everything here is based upon parametrics. It's based upon the standard solid modeling principles. So it's a very simple, easy CAD system to work with. We'll put a quick little face in here where we know that expanded web needs to go. And that being said, we can simply adjust it. So I know it's going to expand out to meet the part. We know that distance, we make an adjustment in the sketch, and then we'll see as that expanded carrier transforms into an opened up, expanded web. Going further along, we can continue to populate the strip. I may add a different station here, any place along the line. Maybe this is going to be the position where I'll have my cutoffs. Maybe I'll add another one, same thing again, but it's going to be where I'm going to punch some holes in. So maybe those holes that go at the very end, because after it's formed, it's going to be a truer way to get that shape. Then here I've got another form I'm going to put in. Maybe I want to put an idle in beside it. It's up to me how I want to position those. Finally, I'll copy that expanded web down the road. You see it fill in that entire strip. So for the amount of time I've spent on this, I've quickly got a strip that I can either use an estimation for and put it in a quote, or going further, I'll start to develop a tool design around it. Since we're talking about tool design, we're dealing with a full-blown parametric, solids-based tool design, fully assembled, in assembly fashion here. So I'm going to go to where I have a pre-configured die set, and it has all the components that I may want to start with. It could be whatever each customer needs it to be. So it could be something as simple as 2 shoes and a bunch of guide pins, the 4 guide pins, or it could be something a little more involved like this one, where I'm actually placing some die steels, I'm placing a stripper plates, material guides. You can see this is a fairly developed die set, everything but the rest of those different progressions. It's shaped itself, formed itself around my current strip, so it knows the overall size of the strip. It understands how high the different Z values are on that strip, how far down the bends are, and it's gone and populated these sizes for me. I have control over each of these. Like here, I've just put in my die set, but I want to get my die plate to be a bit longer here because I want to capture more of those green punch faces and put them all right here on this particular stripper plate. So I'll make some adjustments here. You can see the diagrams help me to understand exactly what each of these values are. All this, again, fully customizable to whatever the needs are of each individual customer. So as I size up my die steel, you note it's stretched out the stripper plate. It's stretched out the location of where my different guide bushings are going to be, where my pneumatic springs are going to be. I might feel those springs are too far apart, or I'm thinking that it's going to go right where I need to place a punch now. So we'll just simply parametrically make a couple edits, move them over so I have room. You can see where it was, where it's moved to, all the different components assembled with it, such as the screws and locators, all that will go with it when I move it. So that looks good. I've made the adjustment. You can see that those green faces are in a safe spot where I can now pull in some different punches. In this case, the first thing I want to do is set up a punch holder for what's going to be a wire EDM'd shape or hold a punch. So here we'll go and pull one in. There's my punch holder. Again, the components go with it. Those are just standard catalog screws and dowels. You got the ability to make a catalog out of anything that you need. Plus, there's an extensive list of different catalog components from well-known vendors, Dadco, Dayton, Tipco, Usimi. The list is very, very extensive, and we're always adding more to it. So I've placed my holder, you see here, right at the base of where the punch is going to come from. Now I'm just step in and say, let's make a couple edits to that. Change the overall sizes. Again, my diagram reminds me what my width X and Y are. There you see it's been adjusted. Screws and dowels go with it. I could further adjust the location if I want. In this case, I'm going to say, let's just go ahead and drop those 2 punches in there. And you can see as I turn this, it's going to take that and turn it about for me as it builds up those different punches. All right, so the punch was initially set up to go a certain distance past the bottom of the coil and then extend down into the die side, and then is going to have a drop, slug drop, going through the back shoe. Each of those parameters were set up originally when we loaded up our setup file. Now we can tell it if we want to make a change or if we want to cut or not cut something. Here it now knows, well, I've got these holders to deal with. So what do I do with them? So my choice is, again, how do I want to cut those? And now it's placed those in for me. And you can see the bottom, how it's got that slug drop. So I've got the land, the die life in the die steel, and then it tapers open 1 degree, 2 degrees, whatever I put in my setup, and then it opens up wide to drop out to the bottom of the shoe. So all my clearances are established and set, and now every punch I pull that way, I know I'm going to have the right configuration, the standard configuration that my shop uses day in and day out. To get a closer look at it, we'll pop this over into a view where it's easier to see. And there you get a good idea now what's involved in it. So here I'm going to now put in some forming steel. I want to capture the shape of these stations and place it into the steel. I'm working again just with the die side. If I were to offset those faces, again, I could do the punch as well, just doing it the same way you see here. So I brought in a forming steel, could make it on the fly if I wanted to. I like to work with the library because then I got all my screws and components with it. So we resized it to fit the overall size. I'm going to now say I want you to work with that particular station or operation. So it brings in that part that had the 2 flanges. Here I did a quick little operation so I can look just at the parts I'm working with. The brown bottom you see is the part of the die steel that sized itself to match what was in the die set, and then the gray, that's going to be the area that I manipulate so that I can capture the geometry of this particular station. Here we're working again with solids, parametrics, but we have a hybrid environment that allows us to work as a full object volume or as an individual sheet. So just going through patiently, picking each one of these flange surfaces, and you can see how it's changing the shape of that die steel. All right, so maybe I got one more to pick out here. There we go. And I'm just going to cut it back to the flange. Simple as that. So this is an open solid, a sheet solid. It doesn't have to be perfectly airtight. You know, there could even be situations where there might be a gap or two. I can work my way through all that. This case, I'm going to grab the open end of my part. I know I need to extend those faces off to the end here. So I'm just doing a simple sweep of a few faces, chaining it along that edge, setting a direction now where I work right through this face. So it comes off of that face clean. Each of these could be tangent, or in this case, I know the bottom and top are. We'll stitch those two together. Again, an incomplete solid that I have that I'm going to work with. We're going to now cut the block so that the shape of that trench is captured into it. Pick that entire object, and there it's cut in. I say, okay, there it is. So I've quickly got my form together. If that's what I want, I'll just go ahead and merge these 2 blocks together. And then going back to the assembly, the die assembly, I'd manipulate those screws so that I could get a longer screw where I need it. All good so far. So go ahead and merge it. Okay, now we go back to our die assembly. There is everything with the strip in place, and keep working my way through this as I go either one assembly at a time or one form at a time. That's just a quick tease of what's involved.
So while Dave continues with that, I can move over to simulation now, and we can take a look at Altair's Inspire form using our geometry to automatically simulate the Op 20 and Op 30 operations. Here you can see the forming limit diagrams or the safety zone plots as it comes down. We have the thickness or thinning plots, and we can zoom in now along those stretch webs that David was talking about wanting to see in the forming. Here's the thinning plots here. It's a good way to validate exactly what has happened in the operations to make sure everything's right. Our pressure pads, our blank holders, and our actions are all working. Back over to you, David.
So just a quick view of drafting. A couple of nice things in particular is the use of templates or automating our drafting. I basically say, I want you to go and make a drawing of this. In this case, I can pull information from the assembly so that I know the overall sizes, anything that's in the data that goes with it. It could be things that have been calculated like die forces. And you can see here, I'm just doing a quick plan view for a quote, what the overall size is going to be like, and also what that strip is going to look like going through each of its different stations. If I were to detail, I can use this utility that allows me to grab chunks of data, several parts at one time, with they're each having their own settings. Maybe I want to detail a die component or a punch component. Well, I'd be looking at a different direction, or maybe here like this wire EDM component, something like that. Further along the way to go with this would be to do some NC. So here I've pulled in my tool library, and I'm working with one of those different form stations, setting up what I want for my offsets and my step overs. This case, we're doing a rough cut, a rough spiral. And as we do it, it's going to know where the stock is, and it's going to target just that stock. So if I come back in here with another rough cut, it'll cut just that remaining stock. Also, it's a smart system. It knows where the holders are. It knows where the vise is. So all that can be identified and then avoided when it comes time to cut it. Here we're doing a finish by limit angle. So as it creeps around like 45 degrees along a fillet, it can transition how it goes about cutting it. So maybe it lace cuts the top flats, but then Z levels those taller sidewalls. Each of these can be controlled too with the size of the tool length. So perhaps I'm starting with a shorter cutter because I want to have more rigidity and I can cut quicker. But then as I get into longer areas, it won't reach. So the system knows enough to then change over to the longer tool that happens to have, a different speed and feed. All of this, of course, can be simulated. Here you're seeing a full machine simulation. It could be just the individual part, like you see a lot of different simulations plot. Let's pull the G code up, and as I go through the rough cut and now through the semi-finish, you can see how it's targeting just those stair steps, just that remaining material condition. Here you see it taking a Z level and then a lace cut for a finish. So all that is controlled so that I get the quality of cut I want. It could be a remachine too, where I go back and pick out those corners. All that is easily programmed and likewise can be saved as what we call a template. So if this is how I cut my forms, save it, save that tool lineup, save all that information, and then just drop it onto the next form that I'm cutting. And it'll apply the same manufacturing techniques to it, the same processes. Here we're going to take a look at the stock. What has been cut, what has yet to be cut. Did we get all the way down to the end? That stock analysis lets me see that it's complete. Another big part of doing a die is, of course, a wire EDM when it comes to those punch holes. Here at our wire EDM, I'm going to set up one of these punches. I just identify that feature area. It's going to be a variable, or in this case, 4-axis cut. We'll tell it what we want to start with. I'm going to rough cut through the tapered area, then come back, do another rough cut on the land, finally come back with a finish cut along the land. So very quickly, that also can be saved as a sequence or template and used again. Now we're going to target the holes. There's a lot in this when you think about what's involved with holes. Set this up as a 3-axis drill program. Tell the system, go find the holes. There they are. Now group them. So it groups them according to the size, diameter, configuration. Is it counterbore? Is it through hole? And then we'll run it through our list of sequences, different operations, like a library of drill hole strategies. If once it's been calculated, it now goes through and sorts this for me. So it's going to do the center drills in all the locations first, instead of doing a center drill here, then a clear hole, and then a through hole. Or if it's, in this case, a counterbore hole, it'll come through and put those counterbores in with a circle mill routine, like you see here, working its way down. It has the capability of doing every type of hole: threaded holes, counterbore, chamfered holes, backward holes, gun drill holes. All those are available, and it organizes the cutter. So if I have like a drill hole, like a 201 hole, that's going to be a clearance hole for a quarter 20 tap, or I'm sorry, a drill hole for a quarter 20 tap, but it can use that 201 somewhere else. It'll do all the 201 holes, then come back and do the next drill. So it's a smart way of doing the automatic drilling.
Great. Thank you, David. So, a very quick demonstration. I want to bring our team back in. Ralph, David, and Mason are online, and I'll switch over to the chat and see if there's any questions from the team. First one's come in. Not sure who wants to handle this one. How do you manage engineering change orders, ECOs?
That's a big question. There could be a lot of things involved. Some can be simple or more complex, right? What we would do is compare the data to start with to see what the changes are, and then we can bring those changes into the existing strip. Maybe redo a form here or there, update that strip, and then other areas like dealing with tool design, that may require remaking different forms or different punches. But the idea is it's all localized. It's not like you have to start over and start building a brand new strip just because a flange changed. It may really only affect one station, so we'll target that station. From there, anything that's changed, like in the tool itself, the actual steels, the NC program will flag it and say, oh, this has changed. What do you want me to do? Finish cutting it? Whatever the case may be. Then you can keep right on going. You've incorporated the engineering change, everything updates, and now you can keep going.
Looks like it's a follow-up to that question where it asks, is the NC integrated?
Yes, exactly. And that touches on that. Like if something does change, like maybe I've roughed the block and somewhere along the line we've changed that forming area, it'll know it and say, okay, do you want me to continue with this? You can go ahead and cut it, just update the part. Or you have to start over, It might be you roughed it, but you're still good. So, it's worth knowing at that point if you can save the steel or not.
Let me see. There's automatic auto drilling. How does it know what size drill to use?
Okay, so it'll be up to me to set up how I want to tackle a certain hole. Like I was talking about, like a quarter 20 tap. I'd want to spot drill it and then do a 201 drill and then do a quarter 20 tap. So every time it now sees that hole, it knows what tool to use because I've just saved the rundown, the tooling rundown. It finds the diameter, the depth, can vary. It could be at the bottom of another hole, all that, So once I've set up the sequence, as we call it, then it will know and it will use that sequence again and again.
Fantastic. Can I make my own catalog parts?
Yes, you sure can. The die set I showed you, that was made from scratch, just because that's the way the customer does their particular die sets. They have those standoff corners, with the blocks that have the bushings in it and the coffin handles. Another die set might just be the plates, They just order the plate with the burnouts in it. So it's just up to you how you want to configure that. You can work with what we have and adjust it or make your own. And then with the components, any component can become a catalog part. That catalog part can have knowledge of the hole that it sits in. So again, the quarter 20, it knows there's a counterbore on the top. It knows that the hole goes on down deeper. The thread goes past the bottom, So that knowledge can be with that component. And then you can put all these components, these catalog parts, into an assembly. So you can place an entire fixture in there, like the steel and the stripper plate. You could have your own mini stripper subassembly, plop it all in there, all the holes, everything, the dowel holes, all goes with it and cuts the hole that it needs for each of those components. So yeah, it's a long answer, but the short answer, I guess, would be yes, you can do your own catalog.
So it appeared that you were seamlessly moving between part mode, assembly mode, part mode, assembly mode, NC, back in. Can you sort of take us through the path that you went down through that?
Okay, so I started with the part being in our die design environment, which is basically our assembly mode. It has just tools specialized there in the menu structure for me to get to all those die functions. And I stayed in that environment when I brought the die set in. So all those different components you saw when they loaded up or when I started changing the size is still right there in assembly. Anytime I could say I want one particular part to be active, and whatever I do to that part affects just that part. Also, I can highlight the part and say, I want you to open this part. So now it pops out of the assembly and goes into individual part mode. And that just makes life a lot easier to look at the part that I'm working with, So when I did the cut of the top of the form and I brought those die faces into the form and cut it, that was in an individual part mode. When I said okay to that, it went back to assembly mode. The rest of the stuff like the drafting, the NC, for the sake of timing, we didn't show you opening up an NC document and then, populating it with the part. But there's like an NC file. There's also a drafting file. So those are their own environments. I would have to either open up the drafting file on top of the assembly file, so I've got two files open in the same session, or maybe start another session. So I've got one session with one file that has the assembly and another session with the drafting file that has the document in it, either way. So you can have as many sessions as you want with as many open files as you want. It's just a matter of what your computer can handle.
Excellent. And I know we mentioned that this will be handled in more detail in a second or third webinar in this series. Springback. How do you manage Springback?
Springback is great. Springback is a very exciting part of what Cimatron offers. So at the beginning, you saw us do the FEA analysis where we looked at the thickening and thinning and what areas are going to wrinkle. We also can do the Springback analysis right at that point. So I hit the crash form, I do my Springback analysis, and I get a good idea of how much those flanges are going to wander out. Okay, we save that information. So I can either use that information down the road when I come to that form and tweak the form, compensate for the Springback right there at that form by basically, compensating inward so it like overbends. That way when the part springs back, it bends back to where it should be, which is like a preliminary, predictive way of doing it. Another way would be, well, I've made the part, here it is. I'll go through and I've diged my points against it, sprayed my cloud of points against it, bring that point cloud in and work with the point cloud to do much the same thing. So using that, I can change that part, compensate using the point cloud. Either way, what I'm doing is I'm not working with STL data. I am working with my CAD file to adjust for the spring back. And that's huge because now it's fully manipulated. I could give that file back to the customer and say, here's what I need to tool it to so that I can compensate for your spring back, anything. So it opens the door wide open for flexibility and working with the spring back problems.
And we have, can we work simultaneously across departments?
Yes, you can collaborate. You could have one guy doing detailed drawings. You could have another guy doing the wire EDM or someone doing NC. You've seen a case where one customer, they'll have the assembly guy working on, one guy will be working on die side, another on the punch side. That's, they have to have the same assembly in front of them so that they can see what everybody's doing. But yeah, you can do that. We have to put more resources on it. It's just a matter of who opened the file first. That's the person that needs to save it, really. But that collaboration is possible. And in some cases, you need to get your overall rough sizes so you can get started while you're still finishing up some of the details. So it really is a sensible way to do it.
Fantastic. Thanks, David. Mason, are you online?
Yep, I'm here.
Yeah, just wondering if you wanted to add anything to any of those topics that David just covered.
No, excellent job, David. You touched on a lot of points. Just a quick note for everybody here. I know we went a little bit fast. There's a lot to uncover. I know a die design, it's kind of impossible to do within an hour, but feel free to reach out. You have a part in mind, you want us to take it through, and we're more than happy to take that through. Just let us know what you want to see. We can schedule that. But well done, David. That was a great job.
Thank you.
Great. And Ralph, I think you're still on board.
Yep, I'm here. Yeah, great job, Dave. Kind of just touched on a bunch of basics, but as Mason was saying, there's much more to the product as far as the designing ability and automation. We're trying to squeeze in as much as we can in 45 minutes, but overall, I think Dave gave a flyby of the product. And if you want to get into details and stuff like that, just reach out and we can set up a separate webinar with you and go through anything you want in detail. That's all I wanted to add, but great job. Great.
So there's a QR code on the bottom left-hand corner of the screen. Feel free to hit that. And there's a form there to fill out if you'd like to get a version of Cimatron to start working, or if you in fact want to start working in a little more detail with our pre-sales team. You can also hit us up on www.cimatron.com and look for this webinar to be posted on our webinar pages in the archives within a day or so. If there's no more questions at this time, I'll thank you all for attending, and please attend part 2 in this 3-part series of Cimatron Die. Thank you.